Let's look at the force on a moving charge in a magnetic field. We have seen that a current carrying conductor, when placed in a magnetic field, experiences force. The current through the conductor is because the motion of charges. Actually, the magnetic field exerts force on these moving charges due to which conductor experience forces. We are interested in calculating the force exerted on the moving charges. Consider the situation figured 14.8, where we see a position of the wire that is carrying current I. Suppose there are n charge carriers per unit volume of the area and that each is moving with the velocity v as shown. We'll now find how long it takes for all charge carriers originally in the wire segment shown to exit through the end area A. The volume of the wire segment is AL because there are n charge carries per unit volume. The number of charge carrier in the segment is NAL. If the charge on a charge carrier is Q, each of it as it crosses the end area will transport a charge Q through it. Assuming the speed of carriers to be v, the carrier entering the left face of the segment takes a time delta t is equal to L upon v to reach the right hand face. During this time, all the charge carriers originally in the segment, namely NAL, will exit through the right hand face as each charge carrier has a charge q. The charge delta q that exists through the end area is time, and time delta t is equal to L upon v is delta q is equal to NALQ. Thus, from the definition of the current I through the conductor is I is equal to delta q upon t. Delta q is equal to NALQ, and delta t is equal to L upon v is equal to NAQV. By equation 14.2, the force on the segment L of the conductor carrying conductor I is given by FL is equal to ILB. Substituting the value of current I, FL is equals to NAQV L into B. In 14.8, it can be seen that the direction of the segment L is the same as the direction of the velocity of the carriers. If L is the unit vector along the segment of the L and V, a unit vector along the velocity vector V, then L is equal to V. VL is equals to V, L vector L is equals to V vector L, V is equal to VL. Substituting the value of VL in equation 14.7, we have FL is equal to NAQVL into B is equals to NALQV into B. NAL is the total number of charge carriers in the segment L, so the force experienced by a single charge carrier is F is equals to FL upon NAL is equal to QV into B. Thus, the force experienced by a single charge carrier moving with the velocity V in the magnetic field strength B as F is equal to Q into V into B. Although the equation 14.8 has been derived with the reference to charge carrier moving in a conductor, but it does not involve any parameter of the conductor. So the equation 14.8 is quite general and it holds for any charge carrier moving in a magnetic field. If the electron is projected in a magnetic field with velocity v, it will experience a force which is given by putting q is equal to minus E in equation 14.8, where E is the magnitude of the electronic charge. F is equals to minus EV into B. In case of proton, F is obtained by putting Q is equal to plus E is equal to plus EV into B. Note that in case of proton or positive charge, the direction of force is given by the direction of vector V into B. Rotate V to coincide with B through the smaller angle of rotation and curl the fingers of right hand in the direction of rotation. Thumb will point in the direction of the force. Thus is illustrated in figure 14.9, in which the proton enters into the magnetic field, as shown in the figure, along the direction of the dotted line. It experiences a force in the upward direction as given by the vector v into b. As a result of this force, proton is deflected upwards. As shown in figure 14.9, the direction of the force on a moving negative charge will be positive to that of the positive charge. Due to this force, the electron is deflected in the downward direction as it enters into the magnetic field. It may be noted that the magnitude of the force on a moving charge carrier is qvb sine theta, where theta is the angle between the velocity of the carrier and the magnitude field. It is maximum when theta is equal to 90, when the charged particle is projected at right angles to the field. It is 0 when theta is equals to 0. A charged particle projected in the direction the field experiences no force.